Welcome to Office Hours with Bill Jennings from Klamath Community College. I want to give you a little video lesson on how to solve equations with rational exponents with the variables. So let's look at these examples that I've got lined out for us today. You have x to the a over b, where a and b could be any integers that you want it to be. Basically, it's a fraction in the exponent. We want to be able to solve these equations. Now, we already know, we have strategies for each one of these types, but we've never really seen it combined. And what I want to do is kind of dissect this question right here. Let's talk about that. That could be written as really x to the 3/2. Well, the 3 and the half, is this really the same thing as saying take the square root of x to the third? If I was to take rational exponents and actually write it as a radical. So if I saw this question as being the square root of x to the third equals 27, instead of having that rational exponent, I think it's actually possible that we would say, oh, I've already seen how to do this. I just square both sides, and then I'd get x to the third equals 27 squared. I'm just going to get big numbers, and hopefully I'll be able to dig my way out of it. But I want to propose that maybe there's a way that we can dig ourselves out of this problem without having to deal with it in multiple steps. Maybe there's a single step to making this go away. The key to being successful to this type of a problem is paying attention to the numerator and the denominator separately and identifying what it is that we're actually going to be doing. Let's look at this one more time, and maybe we'll compare these two together. If I had x to the 3/2, just a second ago we said, hey, that's the square root of x to the third and whatever's going on in the rest of the problem. And we said that's a square root problem. So our strategy to a radical equation is to square both sides, and as a result, we might actually introduce an extraneous solution. And so that's going to be something we have to be paying attention to. At the end of the day, you'll also notice that we would have ended up with x to the third being equal to something. Now that's again a polynomial equation or a higher degree, and you just said, oh, well, it's x to the third, so I'm going to use radicals to back it back down. And so you just said, okay, let's take the third root of that side. Now, when you take the third root of something, it's all good. You just take the positive answer and everything's okay. But if this had been a different example, with it being different than 3/2, we could explore, so to speak. Just ignore this for a second. If I would have had x to the 2/3 instead of the 3/2, let's presume that would have been the other way around. We would have said, hey, that's just the third root of x to the second. And we'd have said, okay, well, let's then raise this to the third power, and then you'd have got x squared equals whatever else is going on. And then you would have said square root. But when you square root, notice what happens is x squared. When you square root, you introduce a plus or minus to the other side of the equation, because when you use the square root property, you get plus or minus. So let's work some of these problems and see how they come out. Okay, so working through this problem, I want to use a little bit of a shortcut. Instead of saying, well, let's take the third root of it and then we'll square it or whatever's going to happen, I can do that all in one step. Notice that this is to the 3/2, and if I had x to the 3/2 and I was to raise it to the 2/3 power, I would actually end up with x to the first, and that's actually my goal. As long as if I introduce a double answer, I've got to take care of that, or an extraneous solution, I just got to be paying attention to it. So I'm going to propose that what we should do right off the bat is, instead of worrying about rewriting it in radical form, let's just do it right here. We can deal with radicals inside of the rational exponent. So let's raise this side to the 2/3 power. If I raise this side to the 2/3 power, x to the 3/2 to the 2/3, the whole reason why I did that is because when we have the power rule on exponents, we multiply those two things together, and I get x to the first, and that's really my goal. And so on the other side, I'll get 27 to the 2/3. Now, we need to be paying attention to what we just did. If I say raise this to the 2/3 power, in one step I'm saying let's square it, and we're going to take the third root of it at the same time, because the 2 is on top, meaning we're squaring it. The 3 is on the bottom, implying a third root. If you take the third root of each side, everything's fine. If you square both sides, you potentially introduce an extraneous solution, and we must check our answer now at the very end of the day. So x equals 27 to the 2/3. Now you can plug it into your calculator, but if we just look at it, this is really saying, what we really should see here is this is a 3 on the bottom, which is a third root. The third root of 27 is 3, and then we square it, which makes 9. So it says that my proposed solution is x equals 9. I can plug that back into my original question and see if it works. 9 to the 3/2 equals 27. You can plug it into your calculator. Yes, it is true, but I did go through the process of checking because I had to, because I potentially introduced an extraneous solution right here at this step when I put that 2 there, because I squared both sides of the equation. Let's take a look at this next one. Now, when we did radical equations, our radical equations was all about setting the radical on one side and getting everything else on the other so I could get rid of that radical. And that's the same strategy we're going to employ here, because technically this is a radical equation. Even though it doesn't have radicals written, that 3 that's hanging out down here, that 3 is actually telling you you're taking the third root. Now, the big thing here is we need to recognize that 3, that 5/3 power, right now is only being applied to the x, because the 8's living on its own out on the side. If the 5/3 applied to the 8, there'd have to be a set of parentheses there. So to deal with the radical equation, we would have got the radical all on one side and get everybody else on the other. So let's do it. I have 8x to the 5/3. I'm going to get the 24 over to the other side, so I'll add 24 to both sides. And now I need to get rid of that 8, because the 8's not part of the radical, so I will divide by 8, and I'll get x to the 5/3, that's a power there, x to the 5/3 equals 3. Now, in order to get rid of that 5/3, I need to power it up, and I'm going to power this side of the equation up to the 3/5. Now, the reason why I choose 3/5, remember the power rule says you multiply those, so 5/3 times 3/5 is going to give me my goal of x to the 1. Now, I can power anything up that I want, but I need to pay attention to what I have just done in blue here. I've raised something to the third power. Well, that doesn't cause any trouble, because that will not introduce an extraneous solution. And I've also taken the 5th root of each side in this 3/5. So I'll just power up this side, and everything's legal as it stands, because up to the 3rd, don't have to check it because I don't have an extraneous solution. Take the 5th root of each side. It does not introduce a plus or minus, only the evens do. And so at the end of the day, I end up with this equals 3 to the 3/5. Now, I could rewrite that as the 5th, you could say, technically, that's the 5th root of 27, if you want to write it in radical form, but 3 to the 3/5 is going to be my answer. Let's look at another question. Now, here I've got x plus 5 to the 2/3 equals 4. Now, I cannot just take that 2/3 and distribute it across, because that 2/3 really applies to the whole thing. What you should be seeing here in your mind's eye is this is x plus 5 squared third rooted. You can't just start saying, oh, that this is the x and this is the 5. It is to the whole thing. So I technically have the radical isolated as it stands. So I'm going to dig myself out of this hole by simply powering each side up to the 3/2. So if I power this up to the 3/2, let's see what happens. Now, let's pay attention to powering something up to the 3/2. Technically, what I've just done is I've raised both sides to the 3rd power. That's okay. That's legal. I can do that whenever I need to, whenever I find it useful to me. I've also taken the square root of both sides. That's legal also. But the thing that it has to happen over here is I actually produce a plus or minus. If you had x squared equals 25 and you took the square root of both sides, you would tell me that the answer is plus or minus 5 because you took the square root. When the second you write that square root, right there, that 2, I've actually written a square root down on my paper the second that I've done that. So I need to be true to that. So I ended up with a plus or minus 4 to the 3/2. Now, what is 4 to the 3/2? Well, You can plug it in your calculator if you need to, but what I'm really saying here is right here, this is the square root. What is the square root of 4? Square root of 4 is 2, and then I'm powering it up to the 3, so this at the end is going to be plus or minus 8. Don't lose that plus or minus because you square rooted both sides. Very important to hang on to that. Well, this is the easy side. X plus 5 to the 2/3 to the 3/2. Why did I power it up to the 3/2? I wanted to get rid of it. So I'm just left with x plus 5. Technically, there's a set of parentheses, but there's nothing to distribute, so it's just an x plus 5. Don't forget here at the end of the day to give yourself the two answers that you get. Subtracting 5 from both sides, I get a negative 5 plus 8, a negative 5 minus 8. So at the end of the day, I get an answer of a negative 3 and a negative 13, and I will have a 2 solution. Do I have to check my answers? Well, let's think about it. I raised everybody to the third power. I did not introduce any extraneous solutions. Is it a good idea to plug those numbers in and check it? You bet. Great idea to plug them in and check it, but you don't have to in this case. One more example for us. I've got x plus 2 to the 5/2 equals negative 1. Now we're getting the hang of it now. This is seen as a radical. It's kind of like a square root of x plus 2 with the 5th power going on. Let's dig ourselves out of this by raising it to the 2/5. Let's raise it to the 2/5. What have I done? I have squared both sides, meaning I must check my answer at the end. I've taken the 5th root of both sides. I don't introduce the plus or minus because I'm taking the 5th root. If you take an odd root, you do not make plus or minus, but I've squared it, so I must check my answer. X plus 2 is what's going to result from this, because that goes away, equals a negative 1 to the 2/5. And I should put that negative 1 inside of that. Negative 1 squared, or I could say the 5th root of negative 1 is a negative 1, and then it gets squared, which makes 1. And if you need to plug that in your calculator, you can. Put a negative 1. Just make sure you put parentheses around that negative 1. And then you take a square it, and then take the 5th root of it, and you will get that. And so x plus 2 equals a negative 1. And so at the end of the day, when I subtract 2, I'll say x equals negative 1. I'm not done with this problem. And the reason why I'm not done with this problem is because right here, I squared both sides of the equation, so I must check my answer. When I go back to check my answer, I'll put a negative 1 plus 2 to the 5/2 equals negative 1. That is the check. Negative 1 plus 2 is a negative 1 to the 5/2 equals negative 1. If you put a negative 1 and try and raise it to the 5/2 and stuff it in your calculator, you're going to get an error. The reason why you get an error, because you can't square root negative 1. Negative 1 to the 5th is a negative 1. Then take its square root. That 2 on the bottom as an exponent means you're square rooting both sides. It will not work. It doesn't come out. And so this answer here, while we did a bunch of beautiful algebra, I'm going to have to throw that answer out and say right here there is no solution, because I proposed there was one solution at the bottom. It didn't check out because of the radical problem of introducing an extraneous solution. So my last problem has no solution. Thanks for watching the video. We'll catch you on the next one.